Hello and welcome to our channel again. So I am Suraj with a new video of mine where we will discuss about a wave equation. Which wave equation? So we have done a quantum mechanics lecture on the Schrodinger wave equation, but this is not a Schrodinger wave equation. This is a normal general wave equations for our macroscopic world, not the equations for the particles like the Schrodinger wave equations. So we are now going to prove wave equations very easily and in a very simple terms. So first of all, what is the general expression for the wave equation? So the general expression for the wave equation is like this, that when we done the part, it is in a partial derivative form. Okay, so the wave equations that we are going to study is in the partial derivative form, just like the Schrodinger wave equations, not like an ordinary differential. Because when I will teach you about the wave functions in the macroscopic and the mechanics, when you deal with the wave functions, it is dependent upon x and t, and just like the Schrodinger wave equation, but it is not complex like the Schrodinger wave equation. It is a very simple wave equation. So now we are going to write out this particular expression, general wave equation it is known as, and we are going to derive that particular wave equations. Maybe in the next video we will understand that what this particular equation might tells us to. So in this video we are more focused on the derivation of our wave equation. So let's start our derivations on the wave equation. So I have written here the formula of the wave equation, which is a partial derivative of y with respect to x is equals to 1 over v square del 2y divided by del t2. So what this expression says, so let's a quick recap of what this equation is trying to say. So this is particularly the equation which tells us that if you write out the equations for any particle which is doing the periodic motion, and if a particle is doing periodic motion, is this particular particle doing the periodic motion, or there is some other particles who are consequently doing the periodic motions constitutes a wave. So this is the formula we can check out by plugging the value of y. We can check if this particular criteria is followed, then we can say that yeah, the equation that we have written is a wave equation. The formula that we have written is a wave equation. So now we are going to prove this particular expression. So first of all, you have to know about some things before knowing about this term. First of all, y. So y is the displacement of the particle. Okay. So in some next video, I will do the detailed analysis on the waves. So for now, y is a displacement of the particle at x and t, at x and t point, because it's considered a wave. So we can find out the position of the particle and also at particular time. So for now you can only understand that y is some sort of displacements of the particle, and it is dependent upon both x and t. Y on x and t we'll discuss in later videos, but now let's imagine that y is a function which is dependent upon x and t, and it is the displacement of the particle from its mean position. Okay, so now let's start our proof on this particular expression. So let's write any of the general wave equation formula. So I'm writing here any of the general wave equation formula. Let's say y is equals to, I will assume you can use cos and sine both. Okay, so this does not make any type of the differences while using the sine and cos. So I am taking cos here. Okay, so I am taking cos here. Let's say a cos, and here is omega t minus kx. So this is our particular expression of displacement of the particle in a wave, when there is a wave. Okay, so this is our particular expression. So now next what we have to do is that we have to differentiate this particular equation with respect to the x. So first of all, I am differentiating this particular function with respect to the x. So I am written as del y by del x is equals to. So the differentiation of this particular quantities we are going to do here. Okay, so what this becomes, you can see here that you can easily do this particular type of the differentiation using the chain rule in the differentiation. If you have studied the chain rule, what exactly chain is, maybe in the later videos I will discuss about the chain rule, but let's start our direct proof. Okay, so the thing is that what we have to do is that here we have to differentiate this particular function with respect to the x. It means according to the chain rule, I am directly going to write out that what will happen. Okay, so the thing is that we have to know, by simply using the product rule we can easily evaluate these types of differentiation. So how we can evaluate is that I'm just going to write down the exact way, the differentiation of x. Okay, so this quantity becomes 1, and what we get is that it will become negative of the Ka, and cos is then plus. Okay, so it will become plus Ka, cos becomes sine here, and omega t minus kx. So let me explain that what I have done. So using the product rule, we have to differentiate first. This is a constant, so take it out. The differentiation of cos is equals to the negative sign, so we put negative, and then differentiation of this particular quantity. So this particular quantity treats constants, it's become 0, and this particular quantity differentiation is equals to the negative k, and then negative, and also here cos negative sign, negative negative become positive, and our double derivative become like this. Okay, so let's evaluate it a bit more like this, that now doing the again this differentiation. So if we are doing again, we'll write the del 2y and del x2 is equals to the, okay, so first of all it will become, let me just explain, take this out from our differentiation sign. Okay, and the differentiation of sign is equals to the cos, so let it write it as ka cos. Okay, so ka cos, and omega t minus kx, again omega t will become 0 and minus kx will become minus k, and it will become minus k square cos omega t minus kx. So after doing the double differentiation, we got our expression like this, which is omega t. Remember, this is omega t, this is minus kx. Okay, so we have done it. Now in parallelly, let me introduce. Okay, so in parallelly, what we have to do, let's imagine this particular term again, a cos, and here is omega t. So here is omega t minus kx. Okay, so again here we are going to differentiate the function now with respect to the t. So now with respect to the t, we are going to differentiate this function. So let's see what will happen. Again, the differentiation of cos x is equals to the negative sign and negative a, and it will become sine here. Okay, so here is a sine. Again, by the chain rule, what the integral of the, what the differential of differentiation of this particular quantity, so the differentiation will become, we have to do differentiation with respect to t such that this kx will become 0. In this case, the omega t becomes 0 because we are dealing with x, but in this case we are dealing with t, so that kx will become 0, and our omega t and t will become 1 after differentiation, and our final expression will become a plus a, because there is minus, and here cos minus, and minus minus a, let me introduce omega sine omega t minus kx. So here is omega. Okay, so a omega, so let me write it a more clear way, that what I have written here. Okay, so let me write it in a more clear way. Yeah, okay, so here we can write it as plus a omega, plus a omegas. Now again doing the double differentiation, which is d2y divided by the d del t2 is equals to the, so okay, so now the double differentiation, again we have to do the differentiation again, if we'll do, it will become just like, if we do the differentiation, this will become minus, and here will become a omega square cos here, and again it is omega t minus k, and here x. So this is our what equations become. So let's say this is our equation number 1, and this is our equation number 1, let's say, and this is our equation number 2, let's say. So now we have to prove our equations, so do some things. Okay, so now what we are going to do is that we have written our thing, and now what we are going, we have to prove our this particular expressions. Okay, so we have to prove our this particular equation dividing, let me write it here, dividing equation. Okay, so we have to divide equation 2, so 1 divided by 2, so we have to divide, it means I am trying to say is that we have to divide del to y, and here is divided by del t2 and divided by del 2y and divided by del x2. So what it will become is that if you will see that these terms a cos omega t minus kx and a cos omega t minus kx are equal and they will cut out each other, and what we are left with is the minus omega square divided by the negative of the k square, because this term here and this term a is here a and here a cos omega t. So these are the similar terms and we can easily cut out, and minus minus will cut out here, and you know that omega square upon k square is equals to the velocity of that particular wave traveling. Okay, so the wave velocity is equals to the omega upon t, and a squaring on both sides will result as v square is equals to the omega square divided by the t square. I'm right? Okay, so now what we can write it, now we can just do some of the more simplification. What we'll use that it will become that del shifting this particular del to y here, what we will get is that del 2 y divided by the del x2 divided by the del 2y, it is del, okay, divided by the del, sorry, here is t not x, sorry, okay, here is t not x. So here is del t square and here is del x square. So okay, new shade, okay. So this our what equation becomes, and it is equals to the velocity square. It is equals to the velocity square. Now what we can do is that we just shift this particular term. We shift this particular term to the right hand side and this particular to the left hand side, and what we are now left is with this thing which is called the del 2y divided by the del t2 1 divided by v square. Okay, and shifting our this term to the right hand side, what we can get is that it is equals to the del 2y divided by the del x2. And you can see here that we have to just prove this equation, and we just prove this equation. And remember that this is a very important equation in the world of physics, because it generally describes that how a wave can be described, how we can describe the particular wave. So this is a very important thing you have to know. Just like Schrodinger equation is a fundamental in the quantum mechanics, this is also very important in the mechanics we are doing with anything. In mechanics, this is very important. In wave, this is very important. In periodic motions, this equations is very important. So this is our very clear-cut description of the wave. If any of equations of y satisfy this equation, we say that y is a wave. Y is a wave. Okay, so this is our simple derivation on the wave equations, for general wave equations for the wave on different types of strings and different types of waves that are traveling. And remember that in electromagnetic waves, when we are dealing with electromagnetic waves, this particular wave equation exactly prove that light is an electromagnetic wave. So this equation is very important in the electromagnetism also. Maybe in the next video we are going to deal with these types of things when we start the series of the modern physics about the electromagnetic waves, electromagnetic inductance and all of this. So this is my video on the derivation of this particular general wave equation. So thank you for watching my video.